Hey IB math students, so here are your notes on section 17C and 17D. So first let's talk about probability notation. So I first want to talk about what is called a union. So it's this symbol that looks like a U, but it's not. And let's draw a Venn diagram to illustrate it. Let's say that in this left circle, here's some event A, and in this right circle, here's some event B. And when we're talking about the union of events happening, we're talking about outcomes that contain both A or B. So that would be contained in either circle or in both of them. Let's kind of write that on the side here. So this contains outcomes in event A or in event B or both, meaning the overlapping section there. So you really specifically want to look for the word or when we're referring to a union. Next, I want to talk about an upside down U that looks like this, and it's called the intersection of two events. And let's draw another little Venn diagram. Here's event A, here's event B. And the intersection is just the overlapping piece here. So it contains outcomes in both A and B. So you specifically want to look for the word and when we're talking about the intersection. So let's take a look at these formulas that are on that little half sheet, that formula sheet that I gave you last chapter. I believe you glued it into your notebook for chapter 16 about statistics. It also had some probability formulas on it, but I just copied them on this sheet for you. So we're going to focus mostly just on 3 of these. First, let's talk about combined events. That's the probability of A or B occurring, and it's equal to the probability of A plus the probability of B minus the probability of A and B, because when you add these together, you would have added in the intersection point 2 times. So let's kind of refer to that for a second to explain it. The subtraction piece is because you have to remove one overlapping intersection. So it doesn't count twice. Okay, then we have mutually exclusive events, which if you remember from last class, that is when there are no outcomes in the intersection. So just to demonstrate what a Venn diagram would look like for mutually exclusive events, it would look something like this. Like if here's event A, here's event B. There's no overlapping intersection points. For example, if event A is the probability of getting ahead if you flip a coin, and B represents tails by flipping a coin. Well, if you're just flipping one coin, A and B can't happen at the same time. There's not going to be an intersection of events. So you could either just get A or just get B. There are no outcomes in the intersection. And that formula, as you see here, is just the probability of A plus the probability of B. We're not going to talk about conditional probabilities today, but we are going to talk about independent events a little bit. And independent events are just when one event does not affect the outcome of another event. And you have to be able to use this formula, you have to be told that events are independent. So I don't think actually, I don't think in our notes we're going to be looking at any independent events. You might have something like this in your assignment today, maybe one problem, I can't remember. But it's just the probability of A and B occurring, and it's just the probability of A times the probability of B. Okay, so let's now look at examples below. We're going to use some of the formulas from above. So it says, for each of the following, find the indicated probability and state whether A and B are mutually exclusive. So for part A, we have the probability of A is 0.5, the probability of B is 0.2, and the probability of A or B is 0.7, and we're trying to find the probability of A and B. So we don't know if these are independent events. We're not told that, so we can't use this formula. But if you look above, we can use the combined events formula. Let's do that. So I'm going to take that formula down here and substitute these values in. So I know that the probability of A or B is 0.7, and it's equal to the probability of A, 0.5, plus the probability of B, 0.2, minus the probability of A and B, A intersection B. So I'm going to quickly solve this. So if I subtract 0.7 on both sides, you'll see that the probability of A and B would just equal 0. That's what we're being asked to find. So what this means, if you get the probability of A and B equals 0, it means that A and B are mutually exclusive events. So it's always if the probability of A and B equals 0. Because that means that there would be no overlapping sections. All right, taking a look at part B, we've got the probability of A is 0.7, B is 0.2. We're trying to find the probability of A or B, and we know the probability of A and B is 0.15. So we're going to use the same formula just to plug those values in. And you should get, if you simplify that, 0.75. And because we are told right here that the probability of A and B is 0.15, that means that these events are not mutually exclusive because it's not equal to 0. So let's write that. So this indicates the events are not mutually exclusive. They're only mutually exclusive if the intersection is 0. All right, and then part C, the probability of A equals 0.3. We're trying to find the probability of B, and the probability of A or B is 0.9, and we know the probability of A and B, the intersection, is 0. So we can also use the same formula. And so if we simplify this, we get the probability of B is 0.6. And since we're shown here that the probability of A and B, the intersection, is 0, then yes, we know that they're mutually exclusive. Okay. Take a look at example 2. If you want to pause this for a second and try to figure it out on your own, that's great too. Otherwise, I'm going to go through this kind of quickly. So Example 2 states an automobile manufacturer estimates the probability of a mechanical defect in the 1-year warranty period is 0.65. The probability of any other defect is 0.35. The probability of encountering both types of defects is 0.2. What's the probability of encountering any type of defect? So let's kind of list out what we know. We are told the probability of a mechanical defect is 0.65. Let's let A, the probability of A, represent a mechanical defect. So we know the probability of A is 0.65. Let's have the probability of B represent the other defect, which we know is 0.35. And let's, I guess that's all the information we have about both type of events, but we do know the probability of encountering both types of events is 0.2. So both types, that would be and, probability of A and B. That's kind of a difficult color to see. Is 0.2. So we're trying to find the probability of any type of defect. So that means the probability of A or B. That's what we're trying to figure out. Sometimes they may not say or. You really kind of have to think about it, what it's asking. So we can just use our combined events formula from above, which is probability of A plus the probability of B minus the probability of A and B. And you end up getting 0.8, or if, I guess I should round to 3 significant figures, 0.800. Okay, so I'm going through this kind of fast, so if you need to pause this at any time, feel free to. All right, now we're going to talk about Venn diagrams. So example 3 states at the start of the flu season, Dr. Ahmed examines 50 patients. Of those 50, 30 have a headache, 24 have a cold, and 16 have both symptoms. Some patients have neither symptoms though. So maybe like they came in for, a twisted ankle or something like that. So we're asked to draw a Venn diagram to represent the situation and determine the number of patients that have neither symptom. So my advice to you is to always start with the intersection, meaning the ones that have both. So let's say that the left circle represents a headache and the right circle represents a cold, and we know that 16 have both symptoms, so we're going to put that in the middle. And then figuring out the other pieces are a little harder, or just a little bit more complex. So we know that 30 have a headache, a total of 30 have a headache, but 16 have a headache and a cold. So 30 minus 16 would mean that 14 would just have a headache. Then we know that 24 have a cold, 24 total, but we know that 16 of those have a cold and a headache. So 24 minus 16 is 8, so just 8 would have just a cold. So we also know that some patients have neither symptom. Once again, maybe they came in for a twisted ankle or a stomach ache or something like that. So what we can do is take 50 and subtract out these numbers, 14, 16, and 8, and you get your leftover with 12 on the outside of those 2 circles that have neither symptom. Okay, so let's take a look at part B. We're going to find the probability that a patient selected at random has only a headache. So let's use proper probability notation. I'm going to do only H for headache. Well, that would just be 14 because the 16 represents headache and cold. So 14 out of a total of 50 patients. So you could leave it like this. Remember, I talked last class about how if you want, you don't have to simplify, or if you'd like, you can. I think that IB likes you too, but on my test that I would give, or a quiz or whatever, I wouldn't. It'd be fine with me if you didn't. But if you simplified it, it'd be 7/25, or you could figure out the decimal or percent if you'd prefer. Okay, on part II, we're trying to figure out what's the probability that they have a headache or a cold. So that's the probability. Let's use a notation. Headache or a cold. Headache union cold. So we can use the combined events formula from the front page, where we take the probability of the first event, which, let's see, the probability of a headache. Well, in total, there's 30 that have a headache, so it'd be 30 out of 50. And we add to that the probability of a cold, which would be 24 out of 50. And we subtract out the intersection of those because we don't want to count it twice. So minus 16 out of 50. And that leaves us with 38 out of 50. Have either a headache or a cold. Or if you wanted to write it as like a percent or simplify the fraction, whatever, if you wanted to write it as a percent, it'd be 76.0% for 3 sig figs. And then on part 3, what's the probability that they do not have cold symptoms? So I'm going to use that notation we learned from last class, the complement. So the probability that it's not a cold. Remember, we use an apostrophe for that. So there's multiple ways to figure this out, but I'm just going to use that formula I showed you, 1 minus the probability of a cold, which would equal 1 minus, well, the probability of a cold, we know, is 24 out of 50. So it would just be 26 out of 50, or simplified 13 out of 25. All right, so taking a look at the last example 4, using the table to create a Venn diagram. So here's kind of a Venn diagram that has a lot of things going on. We're looking at how many students are on the volleyball, basketball, swimming team, and some that are on both volleyball and basketball, volleyball and swim, basketball and swim, and some that are on all 3. So a big hint here is that you always want to start at the intersection of all 3. So I'm going to put 3 in the middle, the intersection of all 3 circles. And let's have this top left circle represent volleyball students, the top right basketball, and the bottom represent swimming students. So you always first want to start with all 3 intersection, and then second, you would start with, or next you would go with the intersection of just 2 of them. I'm just going to go bottom to top. So if there's 4 people that are involved in basketball and swimming, so basketball and swimming, 4 total. Well, 3 of those are involved in all 3. So 4 minus 3 means there'd be 1 that would just be basketball and swimming, because there's 3 others that are involved in basketball, swimming, and volleyball. And then from here, I can fill up the rest. For volleyball and swimming, there's also 4. And there's already 3 that are doing all 3. So there would just also be 1 student who's doing just volleyball and swimming. And lastly, there's 8 students in volleyball and basketball. And there's 3 that are doing all 3, so 8 minus 3 is 5. So there'd be 5 students doing volleyball and basketball. And then from here, lastly, we're going to figure out who is just doing just one sport. So let's start with swimming. There's 10 total, And there's currently 1 plus 3 plus 1. There's 5 students who are doing other sports too. So 10 minus 5 is 5. So it'd be 5 people just doing swimming. For basketball, there's 12. And currently there's 9 students who are doing other as well. So 12 minus 9 is 3. And then we have volleyball. There's 15. And there's currently 9 students doing other sports too. So 15 minus 9 is 6. Okay, before we figure out the probabilities of these situations, let's figure out how many total students there are. So if we just add these up, we'd be counting people twice. But what we can do instead is just add up all the numbers that are in this Venn diagram individually. If you add them all up, you get a total of 24. So that'll help us with part A and B down below. So A says, what's the probability that a student does not play basketball? Okay, let's write that using probability notation. Does not play basketball, so the complement of basketball. Remember, that's 1 minus the probability that someone does play basketball. Well, there's 12 people out of 24 that play basketball, so it's just 1 minus 12 out of 24, which equals 12 out of 24, or 1/2. And then part B, what's the probability that students play basketball or volleyball? So that would be basketball or volleyball, union volleyball. So I can use the combined events formula for that. Remember, that's the probability of A plus probability of B minus probability of A and B. So the probability of basketball is 12 out of 24. The probability of volleyball is 15 out of 24. And then I'm just going to subtract out the intersection of volleyball and basketball, or I could just look at this number over here, 8. So minus 8 out of 24. And that would equal 19 out of 24. Or if you'd prefer to write it as a percent, 79.2. Remember that it's fine to write probabilities as either a fraction, a percent, or a decimal. I typically just leave it as a fraction because then I don't have to use my calculator. All right, if you turn to the next page now, you will see some practice using Venn diagrams. I'd like you to pause this video for maybe 5 minutes and work on just the front of this. I have an answer key on the front whiteboard with a gold magnet for you to check your answers. All right, so now please grab that little sheet on the front table labeled section 17D tree diagrams and glue it with the glue sticks on the front table as well into your notebook just in one corner. I'm trying to save paper, and instead of having you take a long time to write out these examples, I just printed them on small sheets, and we're going to take notes on the side and below of this. Okay, so this is all about tree diagrams. Take a look at example 1. Dawn has many choices of what to choose for lunch in the cafeteria. First, she chooses a main entree of either pizza, sandwich, or a hot dog. Next, she chooses a side of either an apple, French fries, or a banana. Last is her drink of choice of either milk or juice. Dawn has equal chance in any of her choices, which is weird, but it is what it is. So take a look at number 1. It says, what's the probability she will choose pizza, an apple, and milk for lunch? Well, before we answer any of these, let's make a tree diagram on the side here to represent the situation. Okay, so first she chooses a main entree, and there's 3 different options. So let's first make a tree diagram with 3 branches. So she could choose pizza. I'll do P for pizza. She could choose a sandwich, SW for sandwich, or a hot dog, HD for hot dog. And then after that, she chooses a side of either an apple, french fries, or a banana. So 3 options. So let's draw 3 branches after that to represent the sides. And it comes off of each entree. So it could be an apple, so I'll do A for apple, FF for french fries, or a banana. And I'm going to do that off of each entree. And last, she chooses a drink of milk or juice. So off of each of those branches, I'm going to do 2 more branches. So mine's off my paper a little bit, but maybe hopefully yours isn't. So 2 branches off of each one of apple, what was it? Milk or juice. Milk or juice. Okay, so question 1 asks, what's the probability she will choose pizza and apple and milk for lunch? So pizza, an apple, and milk. Well, let's answer that below. So the probability of pizza, apple, and milk would be, you can see there's only that one option, but we need to figure out of how many. So and the nice thing about a tree diagram is it's a visual, and so you can just count how many total branches there are on the end to see what the total is. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there's 18 branches on the end, so that means that's the total possibilities. So the probability of pizza, apple, and milk for lunch is just 1 out of 18. Okay, and then number 2 says, right here. What's the probability she will not choose an apple? So I'm going to write that with probability notation. Not an apple, complement. It's the complement of an apple. So you can do 1 minus the probability of an apple, or since it's a tree diagram and we have the visual, you could just count all the ones that are not apples. So let's see. We could do banana, juice, and milk, so that's 2 options, or french fries, juice, and milk, that's 2 options, so 2 plus 2 is 4. Don't choose these 2 because this one has an apple. There's going to be 4 off of each main entree, and 4 times 3 is 12, so the probability of not choosing an apple would just be 12 out of 18, or 2/3 if you simplify. And then number 3, the probability she will choose french fries and juice. All right, let's try to figure that out. I'll do red for number 3. French fries and juice. So here's french fries and juice. Here's one option. Here's another french fries and juice, another option. And one last french fries and juice. So the probability of french fries and juice is just 3 out of 18. Or if simplified, 1/6. So once again, this is kind of the nice thing about a tree diagram. You can just visually see things and maybe not use a formula. Okay, so let's take a look at example 2 and 3. So example 2 states, if I revise, and I looked it up, revise in British terminology means study, actually. I know we've looked at some other problems like that. So if I study, if I revise, there is an 80% chance I will pass the test, but if I do not revise, there's only a 30% chance of passing. I revised for 3/4 of test. What proportion of tests can I expect to pass? I'm going to do this example below. Okay, so I could either revise or not revise. So I'm just going to draw 2 branches for my tree diagram to start and label 1 revise and 1 not revise, revise apostrophe, thinking about the complement. So it says that I revise for 3/4 of the test, so I'm going to put 0.75 probability next to revise. And then the amount that I don't revise would just be 0.25 or 25% of the time. Remember that all probabilities would add up to 1. Okay, so from there, I could either pass or not pass the test. So I'm going to draw 2 branches off of each of these for passing or not passing. So passing or not passing, a passing apostrophe. So for passing, if I revise, there's an 80% chance I'll pass the test. So I'm going to put a 0.8 next to passing, which would mean that not passing, there's a 20% chance, or a 0.2. If I do not revise, there's only a 30% chance of passing. So I'm going to put a 0.3 probability for not revising and passing, and a 0.7 probability, because it adds to 1, for not revising and not passing. So we're asked, what is the proportion of tests that I can expect to pass? So proportion means percentage. So what I want to do is I want to look at revising and passing plus not revising and passing. So I'm going to add those 2 together because there's 2 scenarios where I could expect to pass. So for this, the probability of passing using probability notation, we can just multiply these events together and then add it to the multiplication of these events together. So I'm going to take 0.75 times 0.8 and add it to 0.25 times 0.3. And that would equal 0.675, or in other words, 67.5%. So the probability that they pass, whether they study or don't study, is 67.5%. All right, lastly, example 3. You are off to soccer and love being the goalkeeper, but that depends on who is coach today. With Coach Sam, the probability of being a goalkeeper is 0.5. With Coach Alex, the probability of being a goalkeeper is 0.3. Sam is coached more often, about 6 out of every 10 games. What's the probability you'll be the goalkeeper today? So let's do a tree diagram below. I wrote pretty big on my page, but you probably wrote smaller and can fit this all on one page. So let's see. To start off, we could have one of 2 coaches, Sam or Alex. So I'm going to draw a tree diagram with 2 branches, Sam or Alex. And Sam is coach 6 out of every 10 games, so 0.6 of the time. That means Alex would be coach the other 40% of the time, 0.4. And then with each coach, there's a possibility that you are goalkeeper or not goalkeeper, goalkeeper apostrophe. So let's put 2 branches off of each coach. So it says with Coach Sam, the probability of being a goalkeeper is 0.5. So the probability of not being a goalkeeper is also 0.5. And then with Coach Alex, it's 0.3. And so the probability of not a goalkeeper is 0.7. So you're trying to figure out what's the probability that you'll be a goalkeeper today. So using probability notation, the probability that you're a goalkeeper today. Well, this is actually a really similar problem to example 2, where there's kind of 2 scenarios. Maybe Sam's going to be a coach and you'll be goalkeeper, or Alex will be a coach and you'll be goalkeeper. So you'll multiply those and add them together. So I'm going to take 0.6 times 0.5 to represent the goalkeeper with Sam. And then we're going to add that to the probability you could be a goalkeeper with Alex, which is 0.4 times 0.3. If you multiply those out, you end up getting 0.42, or 3 significant figures, 0.420, or in other words, 42.0% chance of being a goalkeeper. I went pretty fast through this video, so it wouldn't take an hour long. So once again, feel free to go back and pause it, rewatch different parts of it to finish your notes. Now what I'd like you to do is look on Canvas under the top module and today's date and complete the assignment in class. You might need to finish a bit of it at home.